Welcome back to Sleepy Scientist Stories, where tonight we become architects of infinity itself, weaving dreams from the very fabric of space-time. I'm here with you in this sacred space between waking and dreams, where the boundaries between imagination and reality blur like distant galaxies in the cosmic dawn. Whether you're nestled beneath starlit windows or wrapped in the warm embrace of midnight stillness, you've found your way to exactly where you need to be. Tonight, we're going to build a universe. Not with our hands, but with our understanding. Not with clay or light, but with the invisible threads of mathematics that weave through every atom, every star, every breath of space between the galaxies. And if this journey happens to be too fascinating, too beautiful to let you sleep just yet, well, there are far worse ways to spend the deep hours of night than learning how infinity unfolds from a handful of equations. Before we begin this cosmic meditation, take a moment to let your body settle into whatever surface holds you. Feel the weight of gravity. That same force will soon watch sculpt entire galaxies, gently pulling you toward rest. Let your breathing slow to match the ancient rhythm of stellar formation, where each breath takes 1,000,000 years, and each heartbeat spans the birth and death of suns. If you find wonder in these cosmic lullabies, I invite you to share that wonder. Let others know that here, in this digital campfire of consciousness, minds from around the world gather to dream the same dreams at slightly different hours. Tell me in the comments, where are you listening from? What time cradles you right now? There's something profoundly beautiful about knowing that as you drift towards sleep in New York, someone in Tokyo is awakening to the same stars, the same infinite questions. Now, close your eyes if you can. Let your imagination become a canvas not of sight, but of pure possibility. Picture, if you will, a darkness so complete it makes midnight seem bright. Not the absence of light, but the presence of potential, infinite, patient, waiting. This is where every universe begins, in the mind of a scientist who dares to ask, what if? In the beginning, there is only code, lines of text that seem unremarkable, sitting quietly in computer memory like seeds waiting for spring. But these are no ordinary seeds. These are the compressed dreams of physicists, the mathematical DNA of reality itself, written in languages that speak directly to the silicon hearts of machines. A scientific simulation is not a movie. It's not entertainment dressed up as education. It's something far more profound. It's a prayer written in mathematics, a hymn composed of differential equations, a love letter to the universe asking it to reveal its deepest secrets. Let this resonate, speaking more slowly. When scientists create these digital cosmos, they're not trying to fool anyone into believing pixels are planets. They're doing something far more elegant. They're teaching machines to dream in the language of physics. Every simulated galaxy, every swirling nebula, every collision between cosmic titans, all of it emerges from the same fundamental equations that govern the real universe spinning silently around us right now. Think of it as teaching a computer to paint with gravity instead of light, to sculpt with time instead of clay. The canvas is vast, sometimes larger than our observable universe. The paint is pure mathematics, and the artist is our collective human curiosity, channeled through lines of code that can run for weeks on supercomputers, slowly bringing entire cosmic histories to life. Building emotional connection. There's something almost mystical about watching a simulation unfold. In the beginning, you see only dots scattered across empty space, millions, sometimes billions of them, each representing vast clouds of matter larger than entire solar systems. They appear random, chaotic, meaningless. But then, time begins to flow, and with each passing 1,000,000 years, compressed into seconds of computation, those dots begin to dance. Slowly, so slowly you might miss it. If you're not watching carefully, patterns emerge from the chaos. Matter calls to matter across the void. Gravity, patient and inexorable, begins its eternal work of bringing things together. Paint the visual with words. Filaments stretch across the darkness like the neural pathways of some cosmic mind. Nodes of light appear where multiple streams converge, growing brighter and more complex with each passing eon. Voids, vast, empty chambers larger than anything the human mind can truly comprehend, open up between the growing structures. And suddenly, you're not looking at a computer screen anymore. You're looking at the universe being born. Picture, if you will, a darkness so complete it makes midnight seem bright. Not the absence of light, but the presence of potential, infinite, patient, waiting. This is where every universe begins, in the mind of a scientist who dares to ask, what if? In the beginning, there is only code, lines of text that seem unremarkable, sitting quietly in computer memory like seeds, waiting for spring. But these are no ordinary seeds. These are the compressed dreams of physicists, the mathematical DNA of reality itself, written in languages that speak directly to the silicon hearts of machines. A scientific simulation is not a movie. It's not entertainment dressed up as education. It's something far more profound. It's a prayer written in mathematics, a hymn composed of differential equations, a love letter to the universe asking it to reveal its deepest secrets. When scientists create these digital cosmos, they're not trying to fool anyone into believing pixels are planets. They're doing something far more elegant. They're teaching machines to dream in the language of physics. Every simulated galaxy, every swirling nebula, every collision between cosmic titans, all of it emerges from the same fundamental equations that govern the real universe spinning silently around us right now. Think of it as teaching a computer to paint with gravity instead of light, to sculpt with time instead of clay. The canvas is vast, sometimes larger than our observable universe. The paint is pure mathematics, and the artist is our collective human curiosity, channeled through lines of code that can run for weeks on supercomputers, slowly bringing entire cosmic histories to life. There's something almost mystical about watching a simulation unfold. In the beginning, you see only dots scattered across empty space, millions, sometimes billions of them, each representing vast clouds of matter larger than entire solar systems. They appear random, chaotic, meaningless. But then, time begins to flow, and with each passing million years compressed into seconds of computation, those dots begin to dance. Slowly, so slowly you might miss it if you're not watching carefully, patterns emerge from the chaos. Matter calls to matter across the void. Gravity, patient and inexorable, begins its eternal work of bringing things together. Filaments stretch across the darkness like the neural pathways of some cosmic mind. Nodes of light appear where multiple streams converge, growing brighter and more complex with each passing eon. Voids, vast empty chambers larger than anything the human mind can truly comprehend, open up between the growing structures. And suddenly, you're not looking at a computer screen anymore. You're looking at the universe being born. But how does one teach a machine to dream of galaxies? How do you compress the infinite complexity of the cosmos into something a computer can understand? It begins with a kind of beautiful simplification. Every particle in a cosmic simulation, and there might be billions of them, doesn't represent a single atom. Instead, each one stands for something unimaginably vast, a chunk of matter that might contain entire solar systems, condensed into a single point of mathematical light. These particles are like actors in a play where each performer represents thousands. One particle might embody a dwarf galaxy, another might stand in for a nebula so large that light takes centuries to cross it. They don't look like anything, they're just numbers in a computer's memory. But oh, what stories these numbers tell. Each particle carries within it a universe of information. Its position in three-dimensional space, recorded to extraordinary precision. Its velocity, how fast it's moving and in which direction through the cosmic void. Sometimes its temperature, glowing hot from ancient collisions or cooling in the darkness between stars. Even its chemical composition, the recipe of elements forged in stellar furnaces billions of years ago. But particles alone are just ingredients scattered across an infinite kitchen. They need forces to bring them together. to cook them into something magnificent. And in the cosmic kitchen, there are master chefs whose names we know by heart: gravity, electromagnetism, and the fundamental forces that shape reality itself. Gravity is the great sculptor of the universe, patient, inexorable, working across distances so vast that light itself grows tired, traveling between its influences. In our simulations, gravity follows the same elegant mathematics that Newton glimpsed centuries ago. Every particle attracted to every other particle with a force that depends on their masses and the square of the distance between them. It sounds simple, doesn't it? Almost quaint. But when you have billions of particles, each pulling on billions of others, the mathematics becomes a symphony of such complexity that only the most powerful computers can hope to conduct it. Each particle must feel the gravitational whisper of every other particle, no matter how distant, no matter how faint that whisper might be. To make this computationally possible, scientists have developed elegant shortcuts. Instead of calculating every interaction individually, a task that would take longer than the age of the universe itself, they group distant particles together, treating faraway galaxy clusters as single, massive objects. It's like looking at a forest from a great distance. You don't need to see every leaf to understand the shape of the canopy. But gravity, magnificent as it is, cannot work alone. In the spaces between the great gravitational architectures, other forces hold sway. Electromagnetism governs the behavior of gas and plasma, those tenuous clouds of matter that glow and flow and eventually condense into stars. Hot gas radiates its energy into the cosmic dark, cooling and contracting until gravity can finally claim it. These electromagnetic forces are what make simulations truly come alive. They allow gas to flow like cosmic rivers, to compress into dense knots where stars are born, to expand in great bubbles blown by stellar winds and supernovae. They create the turbulence and complexity that transforms simple gravitational collapse into the rich, chaotic beauty of galaxy formation. And then there is the mystery that haunts every simulation: dark matter, invisible, untouchable, yet comprising most of the mass in every galaxy, every cluster, every large-scale structure in the universe. In our digital cosmos, dark matter particles move like ghosts through the ordinary matter, feeling only gravity's pull, immune to light and heat and electromagnetic force. These dark matter particles form the invisible scaffolding upon which the visible universe is built. They collapse first, creating gravitational wells that later trap and compress ordinary matter. Without dark matter, our simulations produce universes that look nothing like our own, galaxies that form too late or not at all, structures that are too small or too large, a cosmos that fails to match the intricate web of light and shadow. We see through our telescopes. The mathematics that governs all of this is written in the language of differential equations, formulas that describe how things change over time. They tell us how particles move in response to forces, how gas flows and compresses, how energy radiates away into the cosmic background. These equations are often nonlinear, meaning small changes can lead to dramatically different outcomes, like butterflies whose wings can influence the formation of hurricanes, or, in this case, the birth of galaxies. To solve these equations, time itself must be broken into tiny fragments. The computer steps forward through cosmic history in increments of thousands or millions of years, calculating at each moment how every particle should move, how every force should act. The choice of time step is crucial. Too large, and the simulation becomes unstable, reality breaking down into mathematical chaos. Too small, and the calculation would take forever. Cosmic histories stretching longer than the real cosmic history they're trying to simulate. Beneath all of this mathematical machinery lie the fundamental constants of nature. Numbers so precisely tuned that tiny changes would render our universe unrecognizable. The strength of gravity, the speed of light, the mass of the proton, the fine structure constant that governs electromagnetic interactions. These numbers are woven into every calculation, the cosmic constants that set the tempo and rhythm of universal evolution. But even with all this computational power and mathematical sophistication, simulations must make compromises. Some processes are too complex, too chaotic, too dependent on microscopic details to model directly. The way individual stars form within collapsing gas clouds, the precise feedback from supernovae and stellar winds, the intricate dance of magnetic fields in galactic disks. These require what scientists call subgrid models, simplified rules that approximate the average behavior of processes too complex to simulate in full detail. These subgrid models are where the art of simulation reveals itself. They must be carefully calibrated against observations of real galaxies, real star formation, real cosmic processes. Too little feedback from stellar formation and simulated galaxies grow too massive, consuming all their gas in a frenzy of star birth. Too much feedback and galaxy formation shuts down entirely, leaving a universe filled with dark matter halos, but no stars, no light, no complexity. It's a delicate balance, this dance between the known and the unknown, between the processes we understand and those we must approximate. Every simulation is an hypothesis about how the universe works, a mathematical model that can be tested against the real cosmos. When simulations fail to match observations, when they produce galaxies that are too red or too blue, too massive or too sparse, distributed in patterns that don't match what telescopes reveal, they point toward gaps in our understanding. Mystery is yet to be solved. And yet, despite all these approximations and simplifications, something magical happens when you set these digital universes in motion. From the cold mathematics of differential equations and particle interactions, structures emerge that look startlingly, breathtakingly similar to the real universe around us. Cosmic webs stretch across simulated space, their filaments glowing with the light of newborn galaxies. Great clusters form where multiple filaments intersect, their gravitational fields so strong they bend light itself. Voids open up between the structures, vast empty regions where matter is so sparse that entire volumes the size of our local galaxy group contain almost nothing at all. Individual galaxies develop personalities within these simulations. Some grow into great spiral disks, their arms marked by waves of star formation that spiral outward like cosmic hurricanes. Others become elliptical giants, their stars scattered in smooth, featureless distributions. Still others remain small and irregular, their formation interrupted by the gravitational harassment of larger neighbors. These digital galaxies collide and merge, their dark matter halos interpenetrating like ghosts while their stellar populations are scattered and mixed. Gas clouds slam together at tremendous speeds, shocking and heating until they glow with the light of 1 billion suns. Black holes, those ultimate gravitational monsters, grow at the centers of the largest galaxies, feeding on infalling matter and occasionally blazing forth as quasars that outshine entire galaxy clusters. Time flows differently in these simulated universes. Billions of years pass in hours of computation. The formation and evolution of structures that took the real universe most of its 13.8 billion year history to create can be watched unfolding on computer screens in fast forward, like watching flowers bloom in time-lapse photography, except these flowers are galaxies, and the garden is the entire observable cosmos. And perhaps most remarkably of all, these simulations can be rewound and replayed with different initial conditions, different assumptions about dark matter or dark energy, or the processes of star formation. They become time machines that let us explore the paths not taken, the universes that might have been if the cosmic dice had fallen differently in the first moments after the Big Bang. Some simulations explore what would happen if dark energy was stronger or weaker, if the universe expanded faster or slower. Others investigate alternative theories of gravity, different models of dark matter, variations in the properties of ordinary matter itself. Each run is an experiment in cosmic evolution, a test of our theories against the ultimate laboratory, an entire simulated universe. The results of these experiments often surprise their creators. Complex behaviors emerge that no one anticipated, patterns and structures that arise naturally from the interplay of simple physical laws. Galaxies develop in ways that theorists hadn't predicted. Cosmic structures form networks and hierarchies that reveal new principles of organization. The universe, even in simulation, remains full of surprises. This is the profound gift that simulations offer to cosmology. They transform abstract mathematical theories into visual, tangible experience. They let us see the invisible forces that shape the cosmos, watch the slow dance of gravity across billions of years, witness the birth and death of galaxies in the safety of computer memory. But perhaps most importantly, they remind us that the universe is not a static thing, frozen in time like a photograph. It's a dynamic, evolving, ever-changing tapestry of matter and energy, constantly transforming itself according to laws so fundamental and beautiful that they can be captured in mathematics and brought to life in code. Every simulation is both a mirror of the universe and a product of human curiosity. It reflects our current understanding while revealing the boundaries of our knowledge. It shows us not just what the cosmos is, but what we think we know about what it is. And sometimes, gloriously, it shows us that we were wrong, that the universe is stranger and more wonderful than our theories had dared to suggest. As you drift towards sleep tonight, carried by these images of digital cosmos and simulated stars, remember that the real universe around you is no less magnificent than these computer-generated dreams. The same forces that shape galaxies in simulation are at work right now, pulling on every atom in your body, connecting you to the cosmic web that stretches from here to the edge of the observable universe. You are not separate from the cosmos. You are part of it, made of elements forged in stellar cores, shaped by the same gravity that builds galaxies, participating in the same cosmic story that our simulations are trying so desperately to understand. And in that recognition, in that moment of cosmic connection, perhaps we find the deepest purpose of these digital universes, not just to understand the cosmos, but to understand our place within it, to see ourselves not as observers standing outside of nature, but as conscious participants in the greatest story ever told, the story of how the universe came to know itself through beings like us, who can dream of distant galaxies and bring them to life in silicon and code. Sleep well, cosmic dreamer. The real universe will still be here when you wake, just as mysterious and magnificent as the simulations that help us glimpse its secrets. And who knows, perhaps in your dreams tonight, you'll find yourself floating through digital cosmos of your own making, watching galaxies form and stars be born in the infinite laboratory of imagination. The universe is vast and we are small, but we are not insignificant. We are the way the cosmos has learned to think about itself, to wonder at its own beauty, to ask the questions that drive us to build digital universes in search of answers. And that, perhaps, is the most remarkable simulation of all. In the beginning, there was darkness. Not the darkness of space, but the darkness of unknowing. Scientists gazed up at the star-scattered sky, wondering how the universe came to be so beautifully, mysteriously structured. Galaxies spiraled like cosmic pinwheels, connected by invisible threads of light, separated by vast oceans of emptiness. How did such complexity emerge from the simple, smooth beginning described by the Big Bang? The answer would come not from telescopes alone, but from something far more unexpected, from machines that could dream. Imagine, if you will, the first cosmological simulations of the 1970s. Picture primitive computers, their screens glowing amber in darkened laboratories. On these screens, just a few dozen points of light dance slowly across the display, each one representing not a star, but an entire galaxy. These early digital universes were humble things, barely more complex than a child's mobile spinning above a crib. Yet in their simple movements lay the seeds of revelation. The scientists watched, transfixed, as gravity worked its patient magic. The points began to cluster, drawn together by invisible forces. Some grouped into pairs, others formed larger gatherings, and slowly, beautifully, a pattern emerged. It was delicate and intricate, like frost forming on a winter window. Clusters of matter connected by thin, thread-like filaments, with vast empty spaces stretching between them. The universe wasn't just expanding randomly, it was sculpting itself into something magnificent. But these early simulations felt incomplete, like a symphony missing its deepest notes. Something profound was absent from their digital cosmos. The galaxies in these early models moved too slowly, clustered too weakly. The real universe seemed to pulse with hidden energy, held together by forces that remained invisible to human eyes. Then came the revelation that would change everything: dark matter. Picture this mysterious substance. Not dark because it's black, but dark because it refuses to reveal itself to light. It neither glows nor absorbs the photons that paint our visible universe. Yet it tugs on everything with its gravitational embrace, like a cosmic puppeteer pulling strings we cannot see. When scientists began weaving dark matter into their digital tapestries, everything transformed. The simulations awakened with new life, new complexity, new beauty. Dark matter moves through space like a cosmic ghost, interacting only through gravity's gentle touch. In the simulations, it forms vast, spherical halos, invisible shells where dark matter grows dense and patient, and within these phantom cradles, galaxies are born, like pearls nestled in shells made of shadow. This discovery gave the simulations their backbone, their hidden architecture upon which all visible beauty could rest. As computing power blossomed through the 1990s, these digital universes grew ever more magnificent. Scientists could now simulate millions, then billions of particles, each one a tiny actor in a cosmic drama spanning eons. The results were breathtaking. Massive filaments of dark matter stretched across their screens like cosmic highways, connecting galaxy clusters in an infinite web. Shockwaves rippled through gas clouds like pebbles dropped in a celestial pond. The large-scale structure of the universe began to mirror what astronomers saw through their telescopes, not just a theoretical model, but a genuine reflection of reality. But perhaps the most beautiful evolution came when scientists began anchoring their simulations to real observations. They used the cosmic microwave background, that faint ancient glow left over from the Big Bang, to set the initial conditions of their digital worlds. These tiny temperature variations became the seeds from which galaxies and clusters would grow over billions of years. It was as if the simulation was being handed a baby photograph of the universe and asked to predict what that infant cosmos would look like 13 billion years later. The phrase, "universe in a box," became the poetry that described these efforts. Each simulation defined a volume of space, perhaps a cube 100 million light-years across, and populated it with virtual matter. Then, like watching time-lapse photography of a flower blooming, the simulation would evolve this cube over billions of years, step by careful step, according to the laws of physics. Each particle's journey would be calculated, each interaction recorded, each gravitational whisper noted and remembered. These boxed universes revealed wonders beyond imagination. They showed how dark matter halos merged like cosmic dancers, how galaxies fell into clusters like leaves gathering in autumn streams, and how cosmic voids formed between dense regions like bubbles in champagne. They demonstrated the elegant power of gravitational collapse and helped confirm that cold, dark matter was indeed the universe's hidden sculptor. Most remarkably, these simulations became laboratories where impossible experiments could unfold. In the real universe, you cannot rewind time or adjust fundamental constants. You cannot change the amount of dark matter or tweak the expansion rate to see what happens. But in a simulation, you can. You can play Cosmic God, adjusting parameters like an artist mixing colors on a palette, then pressing play to watch your synthetic universe unfold in new and beautiful ways. The early limitations were real: low resolution, simplified physics, heavy reliance on assumptions. But the foundation had been laid with mathematical precision and poetic grace. Scientists had learned that gravity could sculpt complexity from simplicity, that digital tools could reveal patterns too vast, too slow, or too distant to observe directly. What started as mere dots on primitive screens had become something far more powerful, a new way of seeing not just the universe as it is, but the universe as it might have been, or might still become. In the early 2000s, a team of visionary scientists decided to build something wildly ambitious. A digital universe so vast, so detailed, and so thoroughly rooted in modern physics that it would stretch supercomputers to their breaking point. This wasn't science fiction or academic daydreaming, this was real, and it would become one of the most influential simulations in the history of cosmology. Its name whispered reverence, the Millennium Simulation. The Millennium Simulation aimed to capture nothing less than the entire visible universe, not in perfect clarity, but in astonishing detail for its time. Launched in 2005 by the Max Planck Institute in Germany, this digital masterpiece modeled the evolution of cosmic structure from about 400,000 years after the Big Bang all the way to the present day. That's over 13 billion years of expansion, collapse, clumping and reshaping, all compressed into a sprawling numerical ballet that danced across computer screens like Aurora Borealis made of mathematics. To achieve this cosmic symphony, the scientists employed 10 billion particles, not real particles of course, but computational ones, each representing a massive amount of dark matter. Together they mapped out a chunk of the universe 2 billion light-years across. Let that sink into your consciousness, like a stone dropped into a still pond. 2 billion light-years. That's about 1/15 the size of the observable universe, a cube of space so large it encompasses tens of millions of galaxies, all their motions governed by gravity's patient, inexorable pull. Imagine trying to simulate the weather for an entire planet, not just for a week, but for billions of years. The Millennium Simulation accomplished exactly that cosmic feat. But what made it truly special wasn't just its scale, it was the precision, the ambition, and the quietly profound philosophical implications of what it represented. For the first time, scientists could study the cosmic web not as a theoretical construct or a distant telescope image, but as a living, breathing, evolving structure they could examine from every angle. To run a simulation of this magnitude required serious computational muscle. The Millennium Simulation executed on a supercomputer that crunched through gravity's equations for months, updating the position and velocity of every particle again and again as cosmic time ticked forward in small, calculated steps. The output wasn't initially a pretty picture. It was raw data, petabytes of floating point numbers describing where each particle existed at each moment in time. But when this data was processed and visualized, it revealed something extraordinary. A digital version of the large-scale universe that looked hauntingly familiar. Filaments and clusters sprang into view like constellations appearing at twilight. Cosmic voids stretched across the simulated sky like vast, empty cathedrals. It was as if someone had taken a slice of reality, turned it inside out, rebuilt it from first principles, and let it unfold according to the universe's deepest laws. The Millennium Simulation focused solely on dark matter, which makes up the bulk of the universe's mass and dominates cosmic structure formation. Ordinary matter, gas, stars, galaxies, was added later using semi-analytic models, mathematical recipes that decorated the dark matter framework with educated guesses about how galaxies might form, evolve, and die. It was like baking a cake using only the essential ingredients, then decorating it afterward with frosting and sprinkles based on careful observation and theory. The importance of this simulation ripples through cosmology like waves from a dropped stone. It allowed scientists to run virtual surveys of the universe, to pretend to be astronomers inside the simulation, pointing virtual telescopes in any direction to see what structures would appear. These mock observations could be compared to real data, helping identify inconsistencies and gaps in understanding. If a real telescope showed more galaxies than the simulation predicted, it raised flags. Was something missing from the physics? Or was the telescope detecting something unexpected? The simulation also helped settle cosmic debates. There was ongoing tension between warm dark matter and cold dark matter models. Warm dark matter particles move faster, erasing small-scale structure like an eraser smoothing pencil marks. Cold dark matter moves slowly, allowing finer, more delicate clumping. The Millennium Simulation strongly favored cold dark matter, showing it naturally produced the kind of cosmic web astronomers actually observe through their telescopes. The word millennium wasn't just a fancy title, it reflected the scope of the project, spanning cosmic time, illuminating billions of years of evolution, establishing a new benchmark for what was possible. Other researchers began designing follow-up simulations with even more particles, more sophisticated physics, better resolution. But the Millennium Simulation remained the standard bearer, the golden reference point against which all others were measured. Yet, it also raised profound questions that drift through the mind like distant music. If we can simulate the large-scale universe with such startling accuracy, what does this say about our understanding of the cosmos? The simulation worked because it made certain assumptions about dark matter's nature and the universe's initial conditions, assumptions based on the best available data, but still fundamentally educated guesses. Beautiful, complex, extraordinarily informed guesses that happened to work remarkably well. The Millennium simulation also had limitations that kept it humble. It possessed incredible breadth, but relatively coarse resolution. Each particle represented a massive chunk of dark matter, millions of times more massive than our Sun. Smaller structures like individual galaxies were effectively smoothed over, requiring different simulations that traded cosmic volume for exquisite detail. But the visualization produced from Millennium data achieved something rare in theoretical physics. They were genuinely beautiful. Vast webs of light traced invisible structure like frost patterns on cosmic window panes. They didn't just inform, they inspired. Students, scientists, and stargazers could look at these images and feel, in some deep and quiet way, that they were seeing the very bones of reality laid bare. Some joked that the simulation was so detailed we might as well be living inside it, a tongue-in-cheek reference that hints at something quietly profound. If a simulated universe can match our own in structure and behavior, how do we define what's real? The simulation doesn't answer this philosophical riddle, but it makes the question harder to ignore, like a melody that lingers long after the music stops. If the Millennium simulation was a grand sketch of the cosmos, then Illustrious became digital astronomy's Renaissance masterpiece. Launched in 2014 by an international team of astrophysicists, Illustrious took the idea of building a universe and brought it into high definition. It didn't just track dark matter's invisible scaffolding, it modeled how gas flows like cosmic rivers, how stars ignite like celestial candles, how black holes feed like hungry cosmic mouths, and how galaxies evolve like living organisms across billions of years. The visual beauty that emerged made even hardened scientists stop and stare in wonder. Where earlier simulations focused primarily on dark matter and used basic approximations for visible structures, Illustrious sought to show not just where galaxies form, but how they grow, interact, merge, and scatter their starlight across the cosmic dark. The result wasn't just more accurate, it was astonishingly lifelike, like watching the universe's own home movies. Spiral galaxies swirled with graceful arms reaching into darkness. Massive elliptical galaxies glowed with the accumulated fire of ancient stellar collisions. Intergalactic gas streamed and swirled like aurora caught in cosmic tides, painting the space between galaxies with invisible beauty. The numbers behind this artistry were equally impressive. Illustrious simulated a cube of space about 350 million light-years across, using over 12 billion resolution elements. Particles and fluid cells representing gas, dark matter, stars, and black holes. Each element carried its own properties like a cosmic passport: mass, velocity, temperature, chemical composition. As the simulation ran, these properties evolved in response to physics equations governing gravity, hydrodynamics, star formation, radiation, and more. It was like watching a digital universe breathe, stretch, and swirl as it expanded through time, every motion choreographed by the fundamental forces of nature. At Illustrious's heart lay a clever algorithm called a repo, a computational technique that used a moving mesh instead of fixed grid boxes. This flexible grid adapted to matter's flow like a cosmic net that could reshape itself, allowing the simulation to maintain both high accuracy and computational efficiency, even in regions with complex dynamics like star-forming galaxies or turbulent gas clouds. What truly set Illustrious apart wasn't just its visual fidelity, but its ambitious scope. The team ran multiple simulations at different resolutions, carefully balancing size and detail, like an artist choosing between broad brushstrokes and fine details. They included feedback processes from stars and supermassive black holes, cosmic phenomena that play crucial roles in shaping galaxies across cosmic time. When massive stars explode as supernova, they blast energy into their surroundings like cosmic fireworks, stirring gas and slowing further star formation. black holes operate on grander scales, spewing jets of hot gas that can push material out of galaxies altogether, like cosmic winds reshaping the landscape of space itself. These feedback mechanisms are notoriously tricky to model because they occur on small scales, but create effects that ripple across cosmic distances. Illustrious used subgrid models to capture this behavior, allowing the simulation to generate realistic galaxy populations that, when compared to real galaxies from telescopic surveys and deep field images, showed remarkable similarities. The distribution of galaxy shapes, masses and colors lined up with observations like pieces of a cosmic puzzle falling into place. Yet Illustrious wasn't perfect, and its creators acknowledged this with scientific humility. Some galaxies emerged too massive, others too compact. The simulations sometimes overproduce stars in certain environments, a known challenge that reminded researchers how much mystery still dwells in the cosmic web. But perfection wasn't the goal. Progress was. Illustrious demonstrated what became possible when physics, computation and artistry combined in digital harmony. The visualizations created from Illustrious data looked less like scientific plots and more like cosmic paintings. Wisps of gas glowed in false colors that revealed temperature and density. Galaxies twirled and tumbled in kaleidoscopic dances across billions of years. These visuals weren't mere decoration. They helped researchers understand how matter moved, how feedback spread, how different processes shaped structure. But they also had an unexpected side effect. They inspired wonder. People outside the scientific community, artists, educators, poets, dreamers, found themselves drawn to this digital cosmos. Suddenly, cosmological simulations weren't just analytical tools. They were portals into hidden universes, alive with motion and mystery, beauty and meaning. Building on Illustrious's success, the team launched an even more advanced project, Illustrious TNG, short for the next generation. This suite of simulations improved nearly every aspect of the original, like a master painter returning to perfect their greatest work. The largest run, known as TNG 300, covered a volume nearly 10 times larger than the original Illustrious high-resolution simulation. TNG incorporated improved models for magnetic fields that thread through cosmic space, stellar winds that blow from dying stars, galactic feedback that shapes entire galaxies, and chemical enrichment that spreads heavy elements throughout the universe. It even tracked the production of carbon, oxygen, and iron over cosmic time, the very elements that make planets and life possible, following their journey from stellar furnaces to the building blocks of worlds. Illustrious TNG excelled at capturing the diversity of galaxies, producing realistic spirals, lenticulars, irregulars, and massive elliptical systems that matched observations with stunning accuracy. It allowed scientists to study how galaxies evolve in different cosmic environments, isolated in vast voids, packed tightly in clusters, or streaming along the filaments of the cosmic web like travelers on celestial highways. The simulation revealed how galaxies interact with their surroundings through complex dances of matter and energy. They exchange gas like cosmic breathing, trigger starbursts like stellar fireworks, and sometimes quench entirely, going silent after brilliant youth like dying embers cooling in the cosmic night. One of TNG's most striking insights involved supermassive black holes, those mysterious giants lurking at galaxy centers. These aren't just exotic cosmic curiosities, they're active participants in galactic evolution, cosmic conductors orchestrating stellar symphonies across billions of years. The energy released from accreting black holes can heat surrounding gas, shut down star formation, and blow matter into intergalactic space like cosmic hurricanes, reshaping the landscape of reality. Just like its predecessor, Illustrious TNG produced visuals that seemed to hover between rigorous science and transcendent dreamscape. Filaments of dark matter stretched like neural pathways in a cosmic brain. Galaxies blazed like fireflies dancing in infinite darkness. Gas clouds rippled with color-coded temperature maps that painted the invisible universe in shades of wonder. In many ways, these simulations became a form of storytelling, scientific narratives told in the language of physics and code, mathematical poetry that revealed the universe's deepest secrets. Behind all the beauty lay something profoundly scientific. These weren't random guesses at reality, but working hypotheses grounded in observation and theory, digital laboratories where researchers could test ideas, measure outcomes, and explore alternate versions of existence. What happens if star formation becomes more efficient? What if black holes release different amounts of energy? What if dark matter behaves in unexpected ways? With each adjustment and rerun, the simulations became ongoing dialogues between theory and observation, between what we know and what we imagine might be true, between the universe as it is and the universe as it might have been. These magnificent simulations remind us how far human understanding has traveled, from a few dozen particles bouncing around in early computer models to tens of billions of resolution elements tracing galactic evolution across cosmic time. The field has grown exponentially, but with that growth comes a deeper humility, a recognition that each answer reveals new questions, each solved mystery unveils greater wonders waiting to be discovered. As you drift towards sleep, let your mind wander through these digital universes, where mathematics becomes reality and computers dream of galaxies. In the gentle darkness behind your eyelids, imagine vast webs of dark matter stretching across impossible distances, galaxies spinning in their cosmic dance, and scientists working quietly in the night, building universes inside machines, seeking to understand the magnificent mystery of existence itself. The universe continues its ancient expansion, carrying us all forward through time and space, while in laboratories around the world, digital cosmos unfold on computer screens, each simulation a love letter to the cosmic web that connects all things, binding matter and energy, space and time, knowledge and wonder into one magnificent, ever-expanding story of existence. The Silent Symphony, a cosmic bedtime story. Close your eyes and imagine floating in the vast darkness of space, where time moves like honey and stars are born from whispers. Tonight, we journey into the heart of creation itself, where invisible forces sculpt galaxies from nothing more than numbers and dreams. This is the story of how scientists learned to paint with starlight, using mathematics as their brush and the laws of physics as their canvas. In the beginning, there is only data, an endless ocean of floating numbers that drift through digital space like cosmic dust. Each number carries within it the seed of something magnificent, a position in space, a velocity through time, a mass waiting to become matter. These are not mere calculations, but the raw ingredients of entire worlds, sleeping quietly in columns of code until the moment when computation breathes life into them and transforms mathematics into majesty. Watch now as the first stirrings of creation begin. Deep within the quantum realm of processors and memory, particles of information start their eternal dance. Each one carries its own story, where it is, where it's going, how much it weighs in the scales of the universe. They are the building blocks of reality, waiting patiently for gravity to wake them from their digital slumber and guide them toward their cosmic destiny. Gravity arrives like a gentle tide, invisible yet inexorable, reaching across the void to touch each particle with its ancient wisdom. It whispers secrets older than time itself, telling matter where to go, how to move, when to gather together in the darkness. Under gravity's patient guidance, the smallest fluctuations begin to grow, like ripples spreading across the surface of a cosmic pond, each wave carrying the promise of galaxies yet to be born. Feel the slow breathing of the universe as these tiny disturbances in the fabric of space-time begin their transformation. Over millions of years, compressed now into moments of computation, small clumps of matter reach toward each other across the emptiness. They merge and grow, becoming larger, denser, more complex. This is gravitational instability at work, the universe's way of organizing itself from chaos into beauty, creating the dark scaffolding upon which all light will eventually hang. In this realm of shadow and silence, dark matter weaves its invisible web across the cosmos. You cannot see it, cannot touch it, cannot capture it in your hands, yet it is the master architect of everything that will ever shine. Like a patient gardener tending to seeds in fertile soil, dark matter nurtures the growth of cosmic structure, providing the framework within which galaxies will bloom like flowers in an infinite garden. as dark matter. Halos grow denser and more massive. They begin to sing a siren song that calls to ordinary matter across the void. Hydrogen and helium, the primordial breath of the Big Bang, starts its long journey inward, falling like gentle rain into these invisible wells of gravity. As this cosmic precipitation gathers speed, it begins to warm and swirl, creating vast whirlpools of gas that spiral through space like celestial hurricanes. Within the simulation's digital heart, fluid dynamics takes over the story, tracking every eddy and current of this cosmic weather. The gas is no longer passive. It becomes alive with turbulence, compression waves, and thermal energy. Some regions grow cool and dense like morning dew collecting on spiderwebs, while others remain hot and diffuse, breathing in and out with the rhythm of stellar winds and ancient explosions. Then comes the moment of first light, when the simulation must decide where stars are born. This is where physics meets poetry, where rigid equations give way to inspired approximation. Real star formation is chaos incarnate, molecular clouds colliding, magnetic fields wrestling with gravity, shock waves triggering cascade reactions across light years of space. No computer can capture every nuance, so instead, the simulation uses recipes, elegant shortcuts that say, when the conditions are right, when density meets temperature at just the perfect threshold, let there be light. Each star that flickers to life in this digital universe is not a single point of light, but a celebration. Millions or even billions of suns compressed into one shining pixel. These stellar nurseries carry their own DNA, age, mass, metallicity, all the elements that determine how they will live and how they will die. Some will burn quietly for billions of years, while others will rage briefly and brilliantly before exploding in supernova that scatter their enriched atoms back into the cosmic wind. This is the feedback cycle, the universe's way of ensuring that every ending becomes a new beginning. When massive stars die, they return their gift of heavy elements to the interstellar medium, stirring the pot of creation and seeding future generations of stars with the materials needed to build planets, and perhaps life itself. The simulation tracks this cosmic recycling program with mathematical precision, watching as each explosion sends ripples through space that will influence star formation for millions of years to come. Now comes the moment of revelation, when raw numbers transform into visual poetry. The simulation's hidden beauty emerges as scientists translate mass into brightness, temperature into color, density into the subtle gradations of light and shadow that reveal cosmic structure. Spiral arms unfurl like cosmic pinwheels, elliptical galaxies puff out like stellar cotton balls, and streams of gas arc between neighboring systems like aurora dancing across the night sky of space itself. These images are not artistic interpretations, but mathematical truths made visible. The spiral arms were never drawn by human hands. They emerged naturally from the interplay of angular momentum and gravitational collapse, the universe's own aesthetic sense expressing itself through the language of physics. Each color tells a story. Blue regions where young, hot stars are being born, red zones where older, cooler stars have settled into comfortable middle age, and dark lanes where dust and gas wait patiently for their turn to shine. Scientists use these cosmic portraits like cosmic archaeologists, comparing their simulated galaxies to real ones captured by telescopes like Hubble and James Webb. Do the colors match? Do they rotate at the right speeds? Do they contain the proper mix of stellar populations? Each comparison is a test of our understanding, a chance to see if our mathematical models truly capture the essence of cosmic evolution, or if they need refinement, adjustment, a gentle nudge toward greater truth. The most remarkable aspect of these visualizations is how intuitively beautiful they appear. Your brain, evolved to recognize patterns in the natural world around you, immediately grasps the elegant structure of a spiral galaxy or the stately grandeur of an elliptical system. Despite their vast scales and billion-year timelines, galaxies follow forms that feel familiar, like flowers blooming in slow motion or whirlpools forming in a cosmic bathtub. This recognition creates a bridge between the mathematical and the emotional, between scientific understanding and aesthetic appreciation. Sometimes the most wonderful surprises come from the unexpected. Simulations can produce structures that astonish even the researchers who created them. Streams of stars torn from disrupted satellite galaxies, filaments of gas twisted into elegant arcs, voids so vast and pristine they seem to echo with cosmic silence. These are not programmed features but emergent phenomena, natural consequences of the physical laws encoded in the simulation's DNA. This emergence is perhaps the most magical aspect of cosmic simulation. The researchers don't tell the computer how to make a spiral galaxy. They simply encode the laws of physics and let the universe create itself. The spiral arms, the central bulges, the satellite galaxies all arise spontaneously from the interplay of gravity, gas dynamics, and stellar feedback. It's as if the simulation has tapped into the universe's own creative intelligence, allowing it to express its inherent artistry through digital mathematics. To transform these numerical symphonies into visual experiences, scientists use specialized visualization tools that function like cosmic translators. Programs like YT and OpenSpace serve as bridges between raw computation and human perception, applying color maps that make temperature visible, lighting models that simulate how starlight would appear to distant observers, and camera systems that allow virtual journeys through simulated space. The resulting movies are breathtaking, cinematic fly-throughs of virtual galaxies that compress billions of years of evolution into minutes of viewing time. You can coast past stellar nurseries where new suns are being born, dive through spiral arms thick with cosmic dust, and witness galaxy collisions that unfold like slow-motion ballets of light and gravity. In the real universe, these processes would take longer than human civilization has existed. In simulation, they become accessible to your imagination, compressed into human timescales while retaining their cosmic grandeur. But these simulations offer more than just beautiful imagery. They provide windows into possible futures and hidden pasts. A simulated galaxy might reveal the aftermath of a merger we've never observed, or predict the existence of a gas halo that future telescopes might detect. In this way, simulations don't just recreate known reality, they extend it, offering glimpses into the unseen corners of cosmic evolution and suggesting new phenomena for astronomers to seek. Now, let us turn our attention to the universe's greatest mystery: dark matter, the invisible sculptor that shapes everything we see. Imagine trying to paint a landscape where the most important feature is completely transparent. The trees sway in patterns you can observe, the rivers follow courses you can map. But there's something massive and entirely unseen that determines every detail of the scene. This is the challenge scientists face when simulating dark matter, modeling the unmeasurable, computing the invisible. partners in a cosmic dance. But as time progressed, their paths began to diverge. Gas started forming stars, creating feedback loops of energy and matter that changed its behavior. Dark matter, indifferent to these pyrotechnics, continued its patient gravitational choreography, setting the beat for everything else while never itself joining the visible symphony. One of the ongoing mysteries in dark matter simulation involves the nature of the particles themselves. Most models assume cold dark matter, particles that move slowly compared to the speed of light, allowing them to clump efficiently into small structures. But alternative theories propose warm dark matter, with faster-moving particles that smooth out fine-scale structure. These different assumptions lead to different predictions. Cold dark matter creates a universe rich in detail, with countless small galaxies and satellite systems, while warm dark matter produces a smoother, less cluttered cosmos. The choice between these models has real consequences for what we expect to see in the universe. If cold dark matter is correct, the Milky Way should be surrounded by hundreds or thousands of small satellite galaxies. We observe only a few dozen. This missing satellites problem hints that our understanding of dark matter might be incomplete, or that other processes are at work that we haven't yet fully grasped. Dark matter halos themselves have their own complex anatomy, revealed through high-resolution simulations. Rather than smooth spheres, they are lumpy, dynamic structures shaped by countless mergers and interactions over cosmic time. They have dense centers and gradually thinning outer regions, like cosmic cocoons woven from invisible thread. The more massive the halo, the more likely it is to host a large galaxy or cluster of galaxies, and at the heart of nearly every large halo lurks a supermassive black hole, another enigmatic object that seems to thrive in the darkness. The relationship between dark matter halos and the galaxies they contain is one of the most active areas of research in cosmology. Simulations show that this relationship is not simple. It depends on halo mass, formation history, environment, and a host of other factors. Understanding these connections helps astronomers predict where to find different types of galaxies and how they should behave over cosmic time. Despite decades of research and increasingly sophisticated simulations, dark matter remains profoundly mysterious. We've never directly detected a dark matter particle in any laboratory on Earth. We don't know if it's made of WIMPs, axions, sterile neutrinos, or something entirely unexpected. Yet in simulations, it behaves with remarkable consistency, shaping cosmic structure according to gravitational rules we understand very well. Perhaps this is the strangest aspect of dark matter research. The thing we know least about might be the most important component of the universe. It's like trying to understand a symphony while being unable to hear the bass line that holds everything together. You can follow the melody, appreciate the harmonies, but something fundamental is missing from your perception. Only by observing how the visible instruments respond can you infer the presence of that hidden foundation. In our simulations, dark matter comes alive not through light, but through gravity, guiding the visible universe from the shadows like a cosmic puppeteer whose strings are made of space-time itself. We see its influence in every spiral galaxy that spins too fast, every gravitational lens that bends light from distant quasars, every cluster of galaxies held together against the expansion of space. Dark matter speaks to us through the language of motion, the grammar of gravitational attraction, the poetry of cosmic structure. Every simulation begins with choices, and those choices echo through every pixel of the final result. No computer, no matter how powerful, can model every detail of the universe simultaneously. That's not a limitation. It's a fundamental aspect of how science works. Simulations are not perfect mirrors of reality, but rather maps. And like all maps, they must choose what to include and what to leave out, what to emphasize, and what to simplify. Consider resolution, the cosmic equivalent of pixel count in a digital photograph. Every simulation must divide space and time into discrete chunks, particles, grid cells, time steps, and the finer this division, the more detail can be captured. But there are always limits imposed by computing power and time. You cannot simulate every atom in a galaxy, not even every star. Instead, simulations bundle things together, creating representative particles that stand in for millions or billions of individual objects. This means that the finest details of cosmic evolution, the turbulent swirls within molecular clouds, the complex dynamics of individual stellar explosions, the intricate dance of matter around black holes, must be simplified into mathematical recipes called subgrid models. These are elegant approximations that say, when certain conditions are met, we'll assume certain consequences follow, even though the actual physics might be far more complicated. Take star formation, one of the most important processes in galaxy evolution. In reality, it depends on molecular chemistry, magnetic field dynamics, turbulence, dust physics, and countless other factors that operate on scales much smaller than a simulation can resolve. Instead, most simulations use a simple recipe. When gas reaches a certain density and temperature, some fraction of it turns into stars. This approach captures the broad trends of star formation while glossing over the messy details. Similarly, stellar feedback, the way stars influence their surroundings through radiation, stellar winds, and supernova explosions, must be approximated through simplified models. Real stellar feedback is chaotic and varies enormously from star to star, but simulations use average prescriptions that inject energy and momentum into the surrounding gas, according to statistical rules rather than physical first principles. These approximations introduce uncertainties that ripple through every aspect of the simulation. Change the star formation recipe, and you might end up with galaxies that are too blue or too red, too massive or too small. Adjust the feedback parameters, and spiral arms might appear too thick or too thin, central bulges too prominent or too subdued. The art of simulation lies in calibrating these subgrid models to reproduce the observed universe while remaining physically plausible. Different research groups often make different choices about how to implement these processes, leading to simulations that can produce quite different results, even when starting from the same initial conditions. This diversity is actually valuable. It helps scientists understand which features of cosmic evolution are robust, and which depend sensitively on the details of how various processes are modeled. Another crucial choice involves what to include in the simulation at all. Some focus purely on dark matter, tracing the growth of cosmic structure without worrying about gas or stars. Others include gas dynamics but ignore stellar feedback. The most ambitious simulations attempt to model everything: dark matter, gas, stars, black holes, magnetic fields, cosmic rays, and more. Each additional component makes the simulation more realistic, but also more complex and computationally expensive. The temporal resolution of simulations also involves trade-offs. To follow cosmic evolution from the Big Bang to the present requires billions of years of simulated time, but computing resources limit how finely this time can be divided. Most simulations use adaptive time stepping, taking smaller steps when things are changing rapidly and larger steps during quiet periods. But even with these optimizations, important events might be missed or poorly resolved if they happen faster than the simulation's temporal cadence can capture. Boundary conditions present another set of challenges. Simulations must define what happens at their edges. Do galaxies feel gravitational forces from matter beyond the simulation volume? How do cosmic flows enter and exit the modeled region? Different choices can lead to different evolutionary histories for galaxies near the boundaries, introducing artifacts that must be carefully identified and minimized. Despite these limitations and approximations, modern simulations have achieved remarkable success in reproducing key features of the observed universe. The cosmic web, galaxy scaling relations, stellar populations, chemical evolution patterns all emerge naturally from simulations that encode our best understanding of fundamental physics. This success suggests that while we may not have every detail correct, we've captured the essential elements of cosmic evolution. The remaining discrepancies between simulations and observations are actually valuable scientific goldmines. They point toward areas where our understanding is incomplete, where new physics might be hiding, or where improved modeling techniques are needed. The goal is not to create perfect simulations, but rather to build tools that help us understand which aspects of the universe we've figured out and which remain mysterious. Perhaps most importantly, simulations allow us to conduct experiments on the universe itself. We can run the same cosmic evolution multiple times with different parameters, testing how sensitive our results are to various assumptions. We can remove dark matter and see what happens, or turn off stellar feedback, or change the initial conditions. In this way, simulations become laboratories for exploring cosmic what-if scenarios that would be impossible to test any other way. As computational power continues to grow and modeling techniques become more sophisticated, simulations are becoming increasingly realistic and detailed. Future simulations may be able to resolve individual stars in entire galaxies, track the formation of planetary systems, or model the co-evolution of galaxies and their central black holes with unprecedented precision. Each advance brings us closer to a complete understanding of how the universe creates and destroys, builds and breaks, evolves and transforms itself across the vast scales of space and time. The pixels that dance across our screens representing galaxies born from mathematics and nurtured by physical law remind us of something profound. The universe operates according to rules we can understand, at least in part. When we encode those rules into our computers and let them run, entire cosmos bloom in digital space, following patterns so beautiful and natural they seem almost inevitable. In the end, these simulated galaxies are not pretending to be real. They are real, just expressed in a different medium. They are galaxies born of gravity and fluid dynamics, shaped by stellar evolution and dark matter dynamics, painted with the same physical laws that govern the cosmos around us. They speak the fundamental language of the universe, mathematics made manifest, physics transformed into poetry, the eternal dance of matter and energy playing out in silicon and code. As you drift towards sleep tonight, let your mind wander through these digital cosmos, floating past spiral arms that emerged from pure computation, diving through dark matter halos invisible yet essential, witnessing the birth of stars from simple recipes that somehow capture the essence of stellar nurseries. In this realm where numbers become galaxies and equations become evolution, we glimpse something profound about the nature of reality itself. That understanding, even partial and approximate, can be its own form of creation. The universe dreams in mathematics, and through our simulations we dream along with it, painting tomorrow's cosmos with today's equations, one pixel at a time. Simulating a universe is never as simple as drawing a blueprint and pressing go. Every cosmic recipe requires ingredients, but many of them come in uncertain amounts. Researchers begin by tuning the threshold for star formation, deciding when gas becomes dense and cold enough to ignite starlight. It's a practical decision, not always perfect. Set the rules too loosely and galaxies become glittering overachievers. Too tight, and the cosmos grows dark and empty. One of the most delicate ingredients is feedback, how stars and black holes return energy to their surroundings. In the real sky, exploding stars blast gas in all directions, chaotic and unpredictable. Supermassive black holes launch jets that stir and heat gas across thousands of light years. But in simulations, this violent beauty is smoothed down into controlled injections of energy, neat mathematical pulses that sometimes do too little and sometimes too much. Nature is rarely so polite. Some simulations push energy into gas cells only to find the effect barely noticeable. Others sweep entire galaxies clean, halting star formation before it ever begins. Finding the balance is one of the trickiest challenges in cosmic modeling, and feedback isn't the only puzzle. Magnetic fields, those invisible filaments that guide charged particles and shape the motion of gas, are often simplified or left out entirely. Including full magnetohydrodynamics requires enormous computational cost, combining fluid dynamics with magnetic influence. Many models skip it for efficiency. The same goes for cosmic rays, high-energy particles that can travel across galactic scales, subtly heating gas and shaping galactic winds. Including them makes simulations harder to run. But studies now suggest that cosmic rays may play a larger role in star formation than we once assumed. Omitting them might be more than a simplification. It could be a blind spot. Even gravity, the backbone of structure in the cosmos, is sometimes approximated. Most simulations rely on Newton's laws, which work well for most situations. but general relativity reveals that gravity is the curvature of space and time, especially relevant near black holes or in the early universe. Accurately modelling these effects adds layers of complexity, and so many models assume Newton is good enough. But in the deepest gravity wells, good enough might not be true. Chemistry too is simplified. Real gas clouds are not just hydrogen and helium. They carry traces of heavier elements, metals in astronomical terms, spread through space by supernova. These metals cool gas, affect star formation, and colour the light that passes through. But tracking dozens of elements over billions of years would slow even the fastest supercomputers. So many simulations use a single value to represent all metals, glossing over the richness of galactic chemistry. Radiation adds another challenge. Light is more than illumination. It heats, ionizes, and pushes matter. But simulating how radiation flows through space, how it bends around gas, how it changes chemistry and structure, that's an intricate problem. So, many simulations simplify. They treat radiation as a background glow or approximate how it spreads from stars, often ignoring the detailed effects of nearby clusters or shadows cast within clouds. Then there's dark matter. It sculpts galaxies through gravity, yet we still don't know what it is. Simulations assume it is cold and collisionless, because that matches the large-scale universe. But what if dark matter has tiny interactions we haven't seen? What if it's fuzzy, made of waves, or made of multiple kinds of particles? We can't model what we don't know exists. The same is true for dark energy. Most simulations assume a simple cosmological constant, a steady force pulling the universe apart. But if dark energy evolves or interacts with other forces, our models could be missing something profound. Each of these omissions isn't a failure. They're reminders that every simulation is built on choices, a balance between fidelity and feasibility. And in that balance, something beautiful happens, because each gap is a question, a way to test what matters. If adding cosmic rays changes the outcome, that tells us something. If including magnetic fields alters galaxy shapes, that's a clue. Simulations aren't predictions. They're hypotheses dressed in equations, refined over time. Every omission is a doorway to new understanding, and in that way, the gaps are a reflection of our humanity. They show our creativity, our constraints, and our endless curiosity. When you look at a simulated galaxy, you're not just seeing what we know, you're also seeing a monument to everything we haven't figured out yet, and that's where discovery begins. But there's another kind of limitation, one that shapes everything: resolution. In simulations, resolution means how finely space, time, and matter are divided. The higher the resolution, the more detail you see, but the more computational power you need. You can't model the entire universe with the same precision you'd use for a single gas cloud. You'd need a machine the size of a galaxy, and patience that spans ages. So, scientists make a choice. They pick what to focus on, what to simplify, and how to slice the universe into manageable pixels. In large-scale simulations, each grid cell or particle might represent a chunk of space several light-years across. A single galaxy becomes a soft digital smear, recognizable but simplified. That's not a flaw. It's intentional. These simulations are made to understand big patterns, how galaxies form, how they cluster, how dark matter sculpts the web of the cosmos. If you want detail, like the flicker of a star-forming cloud, you zoom in. You trade cosmic scope for local precision. This gives you exquisite resolution, but you lose the larger context. It's like trying to paint the Mona Lisa with a microscope. You get the eyelashes perfect, but miss the smile. Then there's time. Temporal resolution matters too. The universe evolves slowly, but not always. Explosions, mergers, and collapses can happen in bursts. If your simulation skips too many steps, you miss the fireworks. Use too many, and the simulation crawls to a halt. Adaptive time stepping helps. Fast-changing regions get more attention, while empty voids evolve more slowly, but even this technique has limits. Supernova feedback, for example, might look gentle in low resolution. In high resolution, it can be violent, chaotic, even transformative. So, simulations run tests, called convergence checks, at different resolutions. If the galaxy looks stable across scales, the model is trustworthy. If it changes dramatically, there's a problem. Tiny galaxies pose another challenge. In low-resolution models, they vanish entirely, erasing valuable clues about cosmic history and the nature of dark matter. To study them, scientists use zoom-in techniques. They run a big, low-res simulation to find a region of interest, then resimulate that region at high resolution. It's like zooming into a city on a continent-sized map. This hybrid method provides detail and context, but only for one place at a time. If you want to study thousands of galaxies, it becomes too slow. So, researchers now explore new paths, like using machine learning to add fine-grained detail where resolution is low. The idea is to train algorithms on high-res data, then let them fill in the blanks. It's still early, but it could stretch our computing power further, helping us see more with less. In the end, every simulation is a compromise between breadth and detail, between cosmic panorama and intimate structure. Scientists must choose what to capture, what to ignore, and how to shape their digital universe. Yet even with blurry pixels and missing elements, the results are extraordinary. Simulations have shown how structure emerges from chaos, how dark matter weaves the universe, how galaxies grow and change, and how energy feedback sculpts the story of starlight. Resolution may sound like a technical limit, but it's also philosophical. It reflects what we care about, what we want to understand. Some want to trace every whisper in a single cloud. Others want to grasp the melody of billions of galaxies. Neither path is wrong. Both require letting go of perfection. Because cosmic resolution isn't about seeing everything. It's about seeing enough. And enough, when chosen wisely, can reveal wonders. It isn't guesswork. It's a quiet, deliberate dance, an iterative unfolding of insight. A simulation begins with a set of assumptions, stitched from known physics and careful choices. It runs. It produces a digital cosmos. Then, patiently, scientists hold that artificial sky up to the real one and compare. Does the light from simulated galaxies shine with familiar strength? Do stars bloom in rhythms we recognize? If not, the parameters shift. The simulation is run again. Bit by bit, the artificial cosmos aligns itself more closely with reality. Luminosities settle into believable bounds. Gas behaves. Galaxies evolve with a kind of grace that feels less artificial and more alive. But this isn't a victory lap. It's a cautionary line walked with care. Tune your model too tightly, and you risk building not a universe, but a mirror, a cosmos that reflects your biases rather than revealing nature's truths. Calibration is an art, not just a science. A well-tuned simulation doesn't simply match the one variable it was aimed at. It matches others, unbidden, uncalibrated. You might aim to recreate the stellar mass function, how many galaxies exist at each scale, and later discover that the simulation also nailed the gas distribution in clusters, or the quiet rhythm of star formation over time. That's when you know something deeper is working. The simulation isn't a patchwork of fixes. It's a coherent reflection of underlying physics. Still, the process walks a fine edge. Some call it cosmic cheating, a playful jab at the fine-tuning often required to get things just right. You're not forging data, but you are coaxing your creation towards something familiar, and that sparks a philosophical murmur. Are we uncovering truths or scripting them? The answer perhaps is yes. Both. It's discovery through design, understanding born of gentle engineering. We don't know every law. We don't fully grasp the behavior of stars, or the appetite of black holes, or how every photon ripples through gas and dust. So, we build what we can. We shape a model not to be perfect, but to be plausible. And when it resonates, when a simulated spiral galaxy spins at the right speed, glows with the right mix of stars and gas, and arcs across digital space in a form that feels strangely familiar, it's beautiful. Not because it proves we're right, but because it suggests we're close. That, somewhere in the equations and the chaos, we've tuned into a deeper harmony. Calibration, then, is not about control. It's about resonance, like tuning an instrument to join a symphony that was always playing, quietly, cosmically, before we knew how to listen. But what happens when a simulation looks too perfect? When filaments stretch across the dark in just the way our telescopes reveal, and galaxies gather into clusters with an uncanny resemblance to the real universe? Have we confirmed a theory, or staged a well-rehearsed illusion? It's a tension that hums behind every simulated frame, because simulations seem, on the surface, like the ultimate prediction machine. Feed in physics. Wait, watch a digital universe unfold. But the word predict carries a heavy weight. In weather, it means tomorrow's rain. In finance, next week's stock movement. In cosmology, prediction is more abstract. We're not asking where Andromeda will drift next Tuesday. We're asking if structure forms at all, if galaxies grow, if the cosmos we model bears meaningful resemblance to the one we call home. And even this gets complicated. Most simulations aren't built blind. They're tuned with care, using existing observations, luminosity functions, halo mass distributions, the quiet voids between. These are not purely predictive tools. They're rehearsals. They're tests of our theories, replaying the laws of physics to see if they make music we recognize. But here's the deeper question. Once you've rehearsed, can the model surprise you? Can it reveal something you didn't already know? Sometimes, yes. Before cosmic web surveys charted the universe in full, simulations had already predicted a filamentary structure sculpted by dark matter. When telescopes confirmed it, it wasn't just validation, it was vision, a preview born not of observation, but of theory rendered alive. Simulations also let us test the consequences of the unknown. What if dark matter is warm, not cold? What if dark energy changes with time? We can't yet observe these alternate realities, but we can simulate them, let them evolve, let them tell their own stories. If those stories match our sky, perhaps we're onto something. If not, the tale is still worth hearing. And sometimes, simulations reveal the subtler footprints of the physics we do know, like how the breath of a supermassive black hole stirs not just its galaxy, but the wider intergalactic medium, or how a tiny tweak in the early universe's density can cascade into sweeping differences in structure. These aren't predictions in the strict sense. They're consequences, outcomes that emerge when the rules of nature are set in motion and allowed to play. Still, we tread carefully. Just because a simulation matches an observation doesn't mean it predicted it. Correlation is not causation. A model might look right for the wrong reasons. You can simulate a forest and match its canopy, the tree heights, the shadows on the floor. But if your forest is made of ice instead of wood, something is wrong. In cosmology, that kind of error is harder to see. You can't tap on a galaxy to hear if it rings true. That's why simulations are not crystal balls. They are hypothesis engines, tools for asking what if. What if you silence black hole feedback? What if you double star formation? What happens if gravity behaves just a little differently? These experiments don't give you certainties. They give you maps, paths to follow, ideas to refine. And yes, sometimes simulations do stick their necks out. They predict things the sky hasn't yet shown, like massive galaxy clusters at high redshifts, seen first in code and only later through lenses and light. Or the delicate warping of background galaxies by invisible halos, gravitational lensing that was modelled in pixels before it was measured in photons. These moments don't just confirm theory, they inspire. New telescopes, new missions, new eyes turned skyward, seeking what the simulation whispered. But the most humbling thing is how often simulations fail. A model that births too many dwarf galaxies, a feedback mechanism that scours galaxies clean, a star formation history that simply stalls. These are not errors, they're messages. They tell us what we've missed, what we've misunderstood, what still needs tuning. That too is a form of prediction, a forecast that our assumptions may need to change. The universe doesn't owe us convenience. Its truths are not always simple or symmetrical. So when a simulation echoes reality, even approximately, it's a quiet triumph. A sign that we've touched something deep with tools made of math and silicon. So, do simulations predict? Yes, but not always how we expect. They don't tell us the future in days or distances, but they open doors. They give shape to theory, motion to mathematics, consequence to curiosity, and sometimes they point forward toward discoveries not yet made, missions not yet flown, questions not yet asked. And when the observations arrive, we get more than confirmation. We get conversation, a dialogue between expectation and revelation. Simulations rehearse not just data, but understanding. They train our intuition. They stretch our sense of what's plausible. And in doing so, they bring us closer, not just to the cosmos, but to the way it thinks. Underneath it all, there's one more secret ingredient: randomness, a quiet rebellion coded into the heart of every simulation. At first glance, it seems simulations are rigid, deterministic machines tracing inevitable consequences, but randomness hums beneath that order, not as a flaw, but as a truth, because the universe isn't fixed, it's probabilistic. Quantum mechanics guarantees it. Particles don't sit still, they cloud into probabilities. And even on galactic scales, chance shapes everything. When stars ignite, when galaxies collide, which gas cloud gives birth and which one simply drifts. Simulations honor that chaos. They begin with uncertainty, seeded from the cosmic microwave background. Those early fluctuations weren't uniform. They rippled with tiny variations in density, variations we can't map precisely, only statistically. So, each simulation begins with different ripples, different bumps, a new roll of cosmic dice. That randomness sets everything in motion. It determines which galaxies form, which voids stretch, which structures cluster. Change the initial seeds, and the entire universe shifts. No two simulations are identical. Even with the same rules, they produce different universes. Like snowflakes from the same cloud, they're similar, but never the same. One galaxy might swirl gently. Another might splinter in mergers. The recipe is the same, but the outcome is a possibility drawn from a range. Even the births of stars are probabilistic. Gas doesn't always. Turn to light. The simulation calculates a chance, a 30% likelihood this time, maybe 70% next. Feedback too varies. Not every supernova explodes the same way. Black holes don't always feast with equal hunger. Randomness threads through everything. But randomness doesn't mean chaos. It means pattern. It means you can't predict the outcome, but you can predict the distribution. Like flipping a coin 1,000 times. You won't know each result, but you'll know the balance. Simulations use this balance to match the universe, not in detail, but in truth. A simulated galaxy won't match the Milky Way exactly, but a population of them might echo the cosmos we see. The clustering, the brightness, the quiet cadence of starlight. That's what matters. That's where science lives. To be sure, scientists test this. They run suites of simulations, each with different seeds. If a feature appears in all of them, it's probably real, written into the physics. If it fluctuates wildly, it might be an artifact of chance. This ensemble method lets researchers explore not just outcomes but uncertainties. They don't say, this is what happens. They say, this is what could happen, and how likely it is. The real universe is one realization. Simulations show the others. And so, when you see a galaxy bloom in a simulation, or watch filaments stretch across digital voids, remember, you're seeing possibility, not prediction. You're seeing math turned into light, a probability made visible. The cosmos isn't a script, it's a jazz performance with laws, and simulations, for all their order and code, join that song. They don't tell us everything, but they help us hear the harmony behind the noise. They help us understand not just what the universe is, but what it could have been and what it still might be. Let me know if you'd like cinematic thumbnail prompts, SEO-optimized video titles, or a short poetic intro based on this. Here is your full rewrite of the narration in the same length, structure, and order, transformed into a poetic, immersive, and calming voice, suitable for sleepy scientist stories. It preserves all scientific meaning while enhancing the emotional and narrative tone for deep audience engagement. You press run, and the universe begins to breathe. Galaxies blossom into perfect spirals. Voids stretch vast and elegant. Threads of matter lace across space like glowing veins. It's beautiful. For a moment it feels like you've summoned the real thing. But then comes the comparison, the quiet ritual of truth. Telescope data appears, and your heart begins to sink. The real galaxies are chunkier, less graceful. The halos glow more faintly. Something's not quite right, and just like that, your perfect cosmos frays at the edges. But this is not failure. This is how science works, by refusing to rest. A mismatch is not a mistake. It is an invitation, an open door that says, look again. Simulations are not divine blueprints. They are instruments tuned by physics but played by approximation. Built on the scaffolding of known laws, yes, but layered with assumptions, guesses, simplifications. So when a model strays from what the sky reveals, it isn't a defeat, it's a message. A quiet clue that something, somewhere, has not yet been understood. Consider one of the most famous of these mismatches, the missing satellites problem. In early simulations, the Milky Way should have had hundreds of tiny companions, small galaxies each cradled in its own dark matter halo. But the sky didn't agree. Astronomers found only a few dozen. Where were the rest? At first, scientists wondered if the fault lay not with theory but with visibility. Small galaxies are faint, fragile things. Maybe they were simply too dim to spot. As instruments improved and sky surveys reached deeper, more satellites were found. The gap began to shrink, but not enough. So another explanation took root. Perhaps these small dark matter halos did form, but never ignited. Perhaps stellar winds or supernova feedback swept the gas away before stars could be born. In that case, the galaxies would be invisible, silent halos adrift in darkness. A game of cosmic hide and seek. Simulations adapted. The feedback models grew more careful, more complex. The mismatch began to close, not perfectly, but enough to feel the gravity of progress. Another quiet contradiction, the cusp core problem. Simulated dark matter halos like to crowd the center, forming steep peaks in density, sharp cusps at the core. But real dwarf galaxies don't seem to follow suit. Their centers are softer, flatter, more like a gentle hill than a spire. This sparked a deeper question. Is dark matter itself different than we thought? Could it interact, self-scatter, form exotic bonds that soften its distribution? Or perhaps the stars are responsible, stellar feedback erupting in cycles, pushing gas and gravity outward, reshaping the core. The models changed, new versions emerged. Some now produced galaxies with flattened cores, echoing the observational data more closely. The disagreement wasn't an error. It was a doorway. Some mismatches resist repair. The too big to fail problem, for instance. Some dark matter subhalos, according to theory, should be massive enough to form bright, visible galaxies. They are too large, too gravitationally hungry to have failed. And yet, they seem to have. These satellites are missing, not dim, absent. Perhaps the Milky Way's total mass has been overestimated. Or perhaps the efficiency of star formation in those halos has been misunderstood. Or maybe, just maybe, something even stranger lurks in the physics, something the models do not yet contain. These gaps between model and sky are not dead ends. They are pressure points, cracks where discovery begins to push through. Zoom in further, and the tension deepens. Large-scale structure, the grand sweep of galaxies, filaments, clusters, is simulated with breathtaking fidelity. But the small scale, the intimate mess of stars and gas, proves far more elusive. Star formation is turbulent. Gas dynamics are chaotic. Cosmic rays, magnetic fields, radiation pressure, all of it tangled, all of it local. These processes happen on tiny scales, far smaller than the simulation can resolve. So subgrid physics steps in, estimating what happens beneath the surface. But estimations are blunt instruments, and sometimes they miss. Galactic disks become too thin, bulges too puffed. The shape of hydrogen clouds doesn't align. Still, we must be fair. Not all mismatches are born in code. Observations carry their own uncertainties. Dust obscures, light shifts, instruments blur, telescopes peer across billions of years and pass whispers of radiation into meaning. That act alone is a kind of magic, and yet simulations help guide it. They offer alternate skies, born of theory. that can test whether what we see makes sense. If galaxies appear to form stars too fast at early times, simulations can ask, under what conditions does that emerge? Could the universe really behave that way? Or are we misreading the light? And sometimes the simulations get it right first. Before the cosmic web was seen in the sky, it appeared in models, a lattice of dark matter stretching across expanding space. Before baryon acoustic oscillations were measured, their imprint rang through simulated universes. The large-scale structure of clusters, the subtle correlations between galaxies, these were glimpsed in code before they were confirmed in photons. These victories remind us what simulations can do. Forecast, propose, inspire. But they are not oracles. They are conversations. One voice is theory, the other, observation. When they harmonize, knowledge grows. When they clash, wisdom sharpens. They are not rivals. They are dance partners. Observation leads, simulation follows. Then they switch. Telescopes shape the models. Models interpret the data. One corrects the other. One completes the other. And when they stumble, when the steps misalign, we learn. We adjust the rhythm. We listen for a different note. A mismatch is not a misstep. It's an opening, a sign that the dance is still unfolding, that the universe is still keeping time in ways we haven't fully heard. In this sense, disagreement is sacred. It draws a line around what we know and lets us glimpse beyond it. Mismatches are not embarrassment. They are compass points. They steer us, remind us. If every simulation matched reality perfectly, we'd worry we had just painted over our ignorance. But when the universe resists our models, when it misbehaves, it proves that it is not bound by our expectations. It is more surprising, more intricate, more alive. And in the tension between what we predict and what we observe, the future of science quietly waits. At the very beginning, before stars blinked into being, before galaxies took shape, before even atoms had truly formed, the universe was a canvas of potential, rippling, uncertain, alive with chance. Not perfectly smooth, not quite uniform, but close. A sea of almost nothing, stirred by quantum breath. These were not waves in space, they were wrinkles in space-time itself. Quantum fluctuations stretched by inflation to cosmic scales. In those fragile differences lay the blueprint of everything. Inflation, the rapid, almost unimaginable expansion of space in the first moments after the Big Bang, took microscopic uncertainty and painted it across the cosmos. The smallest jitters, usually trapped below perception, were magnified. They became fixed, frozen into the very structure of space. These ripples in density, faint as they were, became seeds. Gravity, patient and tireless, began to pull. Where there was a little more matter, it gathered. Where there was less, it faded. From these barely there beginnings, the entire structure of the universe would emerge. We still see their fingerprints. The cosmic microwave background, a soft bath of ancient light, carries the echo of those ripples. Not sharp lines, but temperature differences, tiny as a few millionths of a degree. Yet those gentle contrasts tell a story of where matter was thick and where it was thin, of where the cosmic web would eventually grow. Simulations start here, with a map, not of our exact universe, but of one statistically similar. A pattern of initial density variations pulled from the same spectrum the CMB reveals. This becomes the framework. Each point in the digital grid holds a value. Denser, sparser, just enough to let gravity know where to begin. And from there, the structure grows. Filaments stretch, voids widen. Clusters form at the nodes where threads meet. The geometry is not random. It mirrors the early ripples, shaped by time, carved by gravity. And to simulate even the dark matter alone, to trace its evolution, takes billions of particles, each one a stand-in for vast clouds of invisible mass. Projects like the Millennium simulation followed over 10 billion particles to map how structure emerges. And that was just the beginning, because dark matter is silent. It pulls, but it does not shine. To see the universe, to compare it to our telescopes, we must add the noisy stuff. Baryons, atoms, gas, stars, light. And that changes everything. Unlike dark matter, baryons interact. They slam, they glow, they cool, they combust, they leave marks. Simulating this requires more than gravity. It demands thermodynamics, radiation physics, hydrodynamics, feedback models. It is in essence controlled chaos. And yet, we try. Because baryons are what we observe. They reveal the structure through their light. Gas falls into dark matter wells. It cools. It forms disks. Stars spark into being. And then the universe begins to push back. Supernova explode. Black holes erupt. The quiet structure becomes a storm. And this is what makes simulations not just valuable, but necessary, because we cannot observe the universe's every moment, but we can let physics play forward. We can watch, rewind, and adjust. Perfect. Continuing your long-form rewrite at the same exact length and structure, here's the transformed poetic version of your latest section, with all meaning preserved and recast in a calming, immersive tone for sleepy scientist stories. A supernova might ripple through a few dozen light-years of space, stirring the gas, shaping the stars, sculpting the silence. But a quasar, a ravenous black hole alight with energy, can reach much farther. Its influence can spread across thousands of light-years, altering entire regions of a galaxy and beyond. The physics that govern these colossal forces are far from simple. Relativistic jets, tangled magnetic fields, radiation pressure, all dance in a choreography too intricate for even our most powerful machines to follow in full. So simulations simplify. They fall back again on subgrid models. Some inject thermal energy, mimicking heat. Others create winds, pushing virtual gas outward. Some even sketch jets into existence, crude but functional. Each of these techniques tries to echo the large-scale consequences of feedback, even if the fine print of microphysics remains unread. And over time, one truth has emerged again and again. Feedback is not optional. It is not decorative. It is central. Without feedback, simulations go off course, not subtly, but dramatically. Star formation races out of control. Galaxies balloon into impossible brightness. The balance unravels. Feedback shapes everything. How quickly stars are born, how large galaxies grow, how bright they shine, how metals spread, how halos form, how galaxies cluster. It is not just a correction, it is a kind of cosmic conversation. Feedback breathes turbulence into order. Supernovae and black holes carve out enormous bubbles in the gas between stars. These voids swell and stretch into the circumgalactic medium, carrying metals and heat far from home. And later, gravity calls some of it back. Gas rains inward again in a galactic fountain, recycled, enriched, ready to try again. Feedback is not just destructive, it regulates, it recycles, it sustains. Without it, galaxies burn too fast, bright, brief lives ending in silence. But with feedback, they smoulder more softly. They stretch their starlight across billions of years. They breathe in slow cycles of birth and rest. Feedback also explains why galaxies are not all alike. It does not act the same in every setting. Some galaxies hold their gas despite repeated supernovae. Others lose it all after a single storm. The strength of gravity, the density of gas, the history of mergers, each shapes how feedback behaves. Simulations that can reflect this diversity come closest to the rich population of galaxies we observe. In massive clusters, feedback operates at scale. Supermassive black holes heat the intergalactic gas, preventing it from collapsing into stars. Without this, clusters would overflow with light. With it, they find balance again. And yet, feedback remains our wild frontier. We've come far from the days when stars formed unchecked, in eager, glowing swarms. But much remains unknown. Different simulation teams use different methods. Some inject thermal energy, others prefer kinetic winds. Some include magnetic fields or cosmic rays. Some leave them out. Even with careful tuning, a model that works for dwarfs may fail for giants. This isn't a failure of simulation. It's a reflection of the complexity we're trying to simulate. Galaxies are not machines. They are ecosystems, dynamic, reactive, full of feedback loops and tangled forces. The laws of physics are clean, but their unfolding in the furnace of galactic evolution is anything but simple. Still, each new generation of simulations takes us closer. From early blunt force approximations to finely tuned multi-channel feedback, the models evolve. And with them, so does our understanding. Galaxies are not passive sculptures molded by gravity. They are participants. They push back. They self-regulate. They adapt. Simulating them is not just tracing their path. It is listening to them, hearing their rhythms of creation and collapse. Through code, we glimpse their pulses. Not perfectly, not entirely, but enough to sense the cosmic breath they ride. Feedback is not just noise, it is a heartbeat echoing across the stars. Imagine standing at the edge of a city skyline, camera in hand. You take a sweeping shot of glowing towers, quiet roads, the whole majestic curve of a metropolis. Then you zoom in. One window, one room, a curtain, a lamp, a cat watching you with mild suspicion. The view is intimate, intricate, and you lose the skyline. This is the trade-off of resolution. You can have the universe or a single galaxy, but not both, not all at once. So scientists choose. Sometimes they zoom in, they stop simulating billions of galaxies and turn to just one. What happens then? Good things. Zooming in means you can afford more precision. You can trace the curling flow of gas, the rising chaos of stellar birth, the tangled arms of a spiral disk. The simulation slows, breathes, deepens. It captures shocks and swirls just a few light years across. Supernova remnants, molecular clouds, feedback loops in stunning detail. These zoom-in simulations usually begin with a large cosmological model. From that wide canvas, scientists pick a region, an interesting halo, a promising structure. They rewind time, trace it back to the early universe, then rerun everything again, but with sharper clarity, focused resolution. It's like zooming in on a single pixel and discovering a whole universe inside. Projects like FIRE, feedback. In realistic environments, use this approach beautifully. They follow galaxies across a range of masses and histories, from tiny dwarfs to majestic Milky Way analogues. FIRE doesn't blur, it simulates. Gas cools realistically. Stars form with complex thresholds. Supernova inject energy in bursts. Winds ripple through the interstellar medium. In these simulations, the galaxy is no longer a statistical smear. It is a living system, pulsing, chaotic, surprising. And that unpredictability is the point. These models test sensitivity. Change the feedback just slightly, and the galaxy becomes something else entirely. Zoom-ins let scientists ask not only how galaxies form, but why they differ. Why one becomes a brilliant spiral and another fades into a dim smudge. Why some galaxies burn fast and die young while others linger. Zoom-ins are also labs for untested physics. They allow researchers to explore how magnetic fields evolve, how cosmic rays stir gas, how star clusters emerge inside dense clouds. These effects are too small, too messy for large-scale runs. But zoom-ins allow the experiment. They let theory stretch its legs. But the cost is steep. These simulations take time, weeks, months, even years. One misstep in a parameter, and the whole simulation may need to be rerun. They are expensive, delicate, and few. Scientists can't simulate hundreds of galaxies this way. They must choose, and that choice introduces bias. If everyone picks galaxies like the Milky Way, we may miss the strange ones, the ellipticals, the ghostly, the irregular. So researchers try to sample more widely. But the labor is immense, and even then, something gets lost, the context. Zoom-ins lack the richness of large-scale structure, the filamentary web, the flow of gas across cosmic scales, the collisions and tides that influence galaxies in their environment. All of that fades into approximation. The region around the galaxy is simulated at lower resolution, a whisper of the world it came from. The galaxy becomes a fish in a tank, not a current in the open sea. Tiny changes in initial conditions, tiny shifts in density, can lead to wildly different outcomes. The butterfly effect, scaled to the stars. And even here, even in these intimate simulations we simplify. We can't simulate every atom. We can't resolve every star. So we use subgrid models again. Parameterizations, assumptions, guesses shaped by theory and observation. This isn't a weakness. It's a reflection of where we are. And still, zoom-ins have transformed our view of galaxy formation. They've shown how feedback sculpts galaxies, how outflows rise and fall, how gas cools, heats, collapses, how star-forming clouds flicker and die. They've also helped us see our own home more clearly. Simulations of Milky Way analogues can be compared directly to Gaia data, star surveys, infrared maps. They let us test whether we are typical, whether our galaxy formed in quiet accretion or violent upheaval, and increasingly zoom-ins let us trace the thread between galaxies and planets. As the resolution improves, we can glimpse the nurseries where solar systems might be born, the flows that deliver water and carbon, the shielding from stellar winds. We're not yet simulating Earth in a cosmological context, but we're getting close. To zoom in is to trade grandeur for intimacy, to leave the cosmic stage and enter a quiet room. And in that room, in the swirl of stars and wind and fire, we learn new languages. Languages that help us tell the here is your full-length rewrite, perfectly matched in structure, word count, and depth, transformed into a poetic, immersive bedtime narration while preserving all scientific meaning and precision. The tone gently mirrors the quiet, introspective style of your sleepy scientist stories channel. The brain doesn't merely receive the world, it constructs it, a painter behind your eyes, layering guesses on reality, filling in gaps, correcting errors, anticipating what might come next. What you see, hear, feel, it's not raw data from the senses, it's a simulation, the brain's best guess at what the world is. This concept, called predictive processing, reshapes how we understand perception. It suggests that your experience of reality is built from models, projections your brain creates, constantly updated against incoming signals. If the data matches prediction, nothing changes. But if there's a mismatch, the model is adjusted. It's an endless loop, quiet, efficient, millions of times a second, across every sense, every breath. Imagine a weather app. It predicts sunshine. But you look out the window. It's raining. The app updates. Now imagine your brain doing this with everything, with touch, with tone, with color and weight and time. That's perception. Vision is a prime example. There's a slight delay, a few milliseconds, between light hitting your retina and your brain interpreting it. But you never notice, because your brain predicts what will be there by the time you notice. It fills in, it edits, it smooths. During rapid eye movements, saccades, you don't see blur, you see stability. Your brain stabilizes the movie, so it always plays fluidly, seamlessly, intelligently. Even your sense of self is a simulation. The brain creates a model of you, your shape, your preferences, your voice, your thoughts. And like all its models, it updates constantly. It adapts to memory, to sensation, to change. That's why, under hypnosis, or in dreams, or during out-of-body experiences, the self can shift, drift, dissolve. The simulation stutters, stretches, or steps aside. And in dreams, the simulation runs wild. Entire worlds spin from silence. Cities, rivers, memories, all rendered in real time with no code, no keyboard, no screen. Just neurons and neurotransmitters, and an ancient imagination unchained. Some neuroscientists believe dreaming is predictive training, a mental rehearsal, a sandbox where the brain tries new things, reorganizes experience, tests reality without consequence. But even when you're awake, simulation is survival. Catching a ball doesn't involve conscious calculation. Your brain predicts its arc. Your hand moves before you know it's moving. When you speak, your brain mutes your own voice slightly, so you don't startle yourself. It even simulates others. That's theory of mind, the ability to guess what someone else believes, intends, or feels. Not because you've measured it, but because your brain builds a model of them too. Sometimes this system breaks down. Illusions reveal the cracks. The hollow mask illusion tricks your brain into seeing a concave face as convex, because your model insists faces must bulge outward. Even when the data says otherwise, your brain refuses to believe. Perception isn't democratic. The brain votes early, and often, and sometimes it gets it gloriously wrong. In conditions like schizophrenia, the line between internal model and external input may blur. A thought becomes a voice. A belief resists correction. In autism, some researchers think predictive processing may weigh data more heavily than expectation. The world becomes too bright, too sudden, too raw, too much input, not enough buffer. But most of this simulation happens unconsciously. You don't think about inertia when you toss your keys. You don't calculate drag when you walk into the wind, but your brain knows. It's learned. It's internalized the physics of the body, the room, the world, not through equations, but through experience. A physics engine embedded in the flesh. It keeps soup from spilling. It balances you on stairs. It lets a dancer spin with precision, and a driver respond before a threat is even recognized. The brain cheats time, not by changing it, but by staying slightly ahead, anticipating. It's elegant. While astrophysicists use machines to simulate galaxies and clusters, your brain does something similar on a smaller, more personal scale. It models a world, navigates uncertainty, adapts to error. It's not exact, but it doesn't need to be. It needs to be useful. That's the genius of it. The brain's simulation isn't about truth. It's about utility. And it works. It works so well we rarely notice it's there. It also explains why we love stories, why we need metaphors, why we build games, write novels, imagine futures. Our minds are simulation machines. We rehearse conversations. We predict reactions. We simulate regrets and daydreams and moral outcomes. And when scientists simulate galaxies or electrons or cells, it's the same idea, just more explicit. A model, a loop, equations instead of neurons, code instead of cortex. But the goal is the same. Simplify the complexity of the world and use that model to understand it. Predict it. Probe it. While a computer simulates dark matter, your mind simulates everything else. Your commute, your relationships, your next breath. Even now, as you read this, your brain is predicting what the next sentence might say and adjusting itself if it's wrong. You don't need a supercomputer to model the universe. You've had one all along, running quietly, since the day you were born. Now, imagine gently a thought drifting in. What if none of this is real? Not like a dream, not a metaphor, not because your charger lies or your alarm clock forgets, but in a deeper, more mathematical sense. What if we're in a simulation? The idea sounds like science fiction, and it is, but it's also philosophy. Serious, strange, statistically rigorous. And it began not with a movie, but with a philosopher, Nick Bostrom. His argument doesn't say we are in a simulation, it says one of three things must be true, a trilemma, a fork in the road. Choose your reality and carry it gently. The logic goes like this. Suppose a civilization becomes advanced enough to simulate entire worlds. Not games, not animations, but minds. Beings that think, feel, suffer, rejoice. Conscious simulations. Now imagine that it becomes easy. Cheap. Efficient. Why stop at one? A civilization might run thousands, millions, to study history, to create art, to test philosophy. If that's true, then most minds, statistically, would exist in simulations. And if most minds are simulated, what are the odds that yours isn't? Hence the trilemma. 1. No civilization ever reaches that level. 2. They do, but choose not to run simulations. 3. They do, and we are in one. No one knows which path is real, but at least one must be. That's the unsettling elegance of it. Not a prophecy, a probability. Of course, there are objections. Some say it's impossible to simulate consciousness, that digital minds can't be real minds. Others doubt that civilizations would survive long enough, or would care to run such things. Perhaps it's unethical, perhaps they're too spiritual, perhaps they just don't bother. And even if simulations are run, perhaps they're incomplete, rendered lazily, like games that only load what the player sees. Some wonder if quantum mechanics hints at that, particles that only collapse when observed. A cosmic shortcut in rendering. But all of this is speculation. And even if it's true, so what? If you're simulated, your feelings are still real. Your joy, your heartbreak, your hunger, your awe, they still shape you. Whether atoms or algorithms, your story still matters. Reality, in practice, is what doesn't go away when you stop believing in it. And this one, whatever it's made of, persists. Still, the idea lingers. If we are in a simulation, is there a programmer, a watcher, a cosmic coder who reads our dreams? Would they be kind, indifferent, amused? Would they ever fix the weather? But perhaps that's not the point. The simulation hypothesis isn't about paranoia. It's about perspective. Like cosmological simulations help us understand galaxies by building them. This thought experiment helps us understand ourselves by imagining we could be built. It stretches the edges of thought. It flips reality inside out. It asks, what does it mean to be conscious? And how much of that can we trust? Some researchers have even proposed tests, looking for digital seams in the cosmic background, pixelation in radiation, patterns that hint at computation underneath. So far, no luck. Reality holds. The stars don't glitch. Gravity doesn't lag. The sky doesn't flicker. If we are inside something, it's exquisitely crafted. And maybe that's all we need to know. Because even if we can't escape the simulation or prove it, the act of imagining it expands us. It reminds us that our deepest assumptions can be questioned, that even when the world feels solid, we can still ask, what if? And that might be the most human question of all, to live as if it's real, to wonder if it's not, to search for meaning, even if it might be programmed into the stars. Somewhere, right now, a simulation of a galaxy runs in a quiet room. Gas swirls, stars ignite, black holes, exhale digital storms. A researcher watches it unfold, and maybe, just maybe, the galaxy watches back, not because it knows, but because the code sings, of course. Here is the full-length rewritten version in a deeply poetic, calming, immersive tone for bedtime science storytelling. The structure, meaning, and word count have been carefully preserved. It offers something more than data, a way to see, to feel, to imagine the cosmos through quiet movement and light. A single swirl in a simulation may hold more than numbers. It may whisper beauty. Not all of it is exact. Not all of it is true. And that's what makes it powerful, because even the flawed ones spark wonder, and wonder is the gateway, not the end, of learning. That moment someone leans in and quietly asks, how does this even work? That's the beginning of everything. So no, simulations were never meant to be perfect, not matching each pixel, not predicting every curve, but they must be honest. They must be willing to show their seams, reveal their errors, correct themselves, and fail in ways that teach. In that spirit, a simulation becomes something gentler, not an answer, but a sketch, not a certainty, but a reaching, a gesture into something far larger than code or math or silicon alone can contain. And when they're wrong, especially when they're wrong, they become even more vital. Because each new version of the cosmos built in code is also a version of ourselves, our patterns, our blind spots, our brilliance, and our biases. To simulate is not just to map the sky, it is to map the mind that draws it. And somewhere, inside quiet machines, galaxies bloom, stars collide, and dark matter drapes across invisible scaffolds. But this is no ordinary calculation. It learns as it unfolds. It predicts without being told. It adjusts to futures no human has yet imagined. And this is the new frontier. Simulations are no longer simply growing larger, though they are. Millions more particles, galaxies captured in finer detail, years spun forward in seconds. But size is only part of the revolution. What's changing is deeper. Who builds them? How they think? What kinds of questions they even dare to ask? We've come far, from single galaxy cubes to entire observable universes, modeled with quiet precision. And these models are beginning to hold more: radiation, magnetic fields, chemistry, feedback that echoes across time. The lines are dissolving. Micro and macro are blending. Starbirths inside collapsing clouds now ripple through whole galaxy clusters. And to make sense of that, we need more than brute force. We need subtlety, a way to treat each particle as a story, each moment as a thread woven into something vast. That's why the architecture of simulation is evolving, not just in speed, but in intelligence. Where once scientists wrote every rule by hand, now learning systems join them. Trained on deep data, past runs, and real skies, these neural tools optimize models, fill in gaps, find patterns we didn't program. Like quiet apprentices, fast, tireless, never in need of rest. And their most profound impact may be in the smallest places. Because beneath every simulation lies the subgrid, the unseen processes, the starbirths, the black hole feeds. Once modeled by rough approximations, these now become playgrounds for AI. We no longer guess the behavior. We let it emerge. From observation, from resolution, from detail learned, not dictated. It's not a surrender of understanding. It's a shortcut to deeper truth. And then, something stranger still. Entire simulations not grounded in physical equations, but in resemblance, generated by AI to mimic reality and form, not force. Digital twins that match observations statistically, useful in training tools and testing theories. These are dreams of the universe. Eerily familiar, uncannily precise. Not true perhaps, but real enough to teach. And then we flip the paradigm again, into the quantum. Quantum simulation does not describe quantum systems, it becomes them. A quantum computer, still young, simulates what classical machines cannot touch. Early universe entanglements, exotic particle interactions, whole fields too rich for bits and bytes. It is like asking a flame to explain heat instead of drawing it with chalk. In time, this may show us how space-time was seeded, how nothingness rippled into stars. Equations once too wild to ride may now be surfed like waves. Even the interface is changing. We no longer just watch simulations. We step inside them. Through virtual spaces, researchers now walk galaxies, touch magnetic strands, swim through the shattered echoes of ancient stars. It's not just spectacle, it's pattern finding, it's intuition, it's discovery made with the body as much as the mind. And with it, a quiet shift occurs. A simulation begins to feel less like a tool and more like a partner. Because what happens when your model surprises you? When it teaches something you didn't put in, it asks more than technical questions. It grazes the edge of creativity, of collaboration, of machine as co-thinker. This challenges more than the method. It reorders the story. Traditionally, we start with theory. We build models. We predict. We observe. But simulations now often flip that. They run first. They reveal. Then we try to explain. This is not disorder. It's a new kind of order. Discovery before expectation. And it changes the rhythm of science. Alongside this, science itself is opening, no longer held tightly. Simulations today span continents, shared machines, shared code, open access, open minds. The universe is too large for any one person to model, but not too large for many to share. And as that culture spreads, so do the models. Bigger, deeper, stranger. Some scientists spend more time exploring simulation data than generating it. These digital skies have become their own form of astronomy, a new kind of observation, where stars are born not in fire, but in code. And still, the most powerful part remains the unknown. We don't know what the next simulation will reveal, and that's the sign of a truly powerful tool. The best models do not confirm, they surprise. They open tunnels to ideas no one saw coming. They become bridges to science not yet written. The line between simulation and exploration is dissolving. We may soon treat digital universes as real playgrounds of inquiry, not just mirrors but laboratories, places where questions breathe, where models speak back, where the imagined shapes the possible, and one day Someone will launch a simulation so rich, so strange, so alive with emergent patterns that they'll pause and ask, gently, almost whispering, "Who's simulating whom?" Imagine standing in front of that model, a canvas beyond end, galaxies dancing like ink in water, dark matter threading invisible lines. No single view can hold it, but you trace its contours, you sketch it with numbers, you draw not with certainty, but with care. This is what simulations do. They approximate, they suggest, they offer not the thing itself, but the closest whisper, and that whisper matters, because even a sketch can hold truth, not by being exact, but by being honest. A sketch owns its incompleteness, its strokes are open to revision, its guesses are marked in every angle, yet it speaks. And what it says about movement, structure, connection, sometimes eludes even the clearest photograph. Simulations do the same. They lift the invisible into shape. They show how chaos dances into structure, how stars respond to silence and force. They reveal the logic of becoming, the how beneath the what, a rehearsal for the real, not to perfect it, but to prepare for understanding. This doesn't mean reality is digital. Physics is not made of bits, but it is obedient to rules. And those rules, constants, symmetries, balances, they can be played, like a melody on cosmic strings, and we do play them. With each new run, we alter the tempo. Try a different key. Watch the universe respond, not always perfectly, and not always predictably, but meaningfully. Because sometimes what looks wrong is actually what opens the door. A perfect model is suspicious. The universe has noise, has mess, has surprises, and good simulations embrace that. They wander through nearby possibilities, not final drafts, but rehearsals of what could have been. And maybe that's why we love them, because we too are rehearsals. Every human thought runs on simulation. Every choice is modeled before it is made. What if I said this? What if I didn't? The brain is not precise, but it sketches, and it sketches enough. In this, simulations become mirrors, not just of stars, but of minds. The way we imagine, the way we hope, the way we build understanding from shadows. And not every sketch is saved. Many fail. Some teach little, others much more. But all of them leave marks, and those marks guide the next rehearsal. In that way, nothing is lost. Even failure is progress. Even silence is a kind of answer. To simulate is to admit we do not know, but we care to ask. We dare to build something incomplete and call it beautiful. We learn, we guess. We render the cosmos pixel by pixel, equation by equation, not because it makes us gods, but because it keeps us curious. Maybe the universe is not made of math, but it listens to it, and in that listening we find rhythm. And so we return again. The simulation restarts, the parameters shift, the resolution improves, a new question stirs, and as our digital universes expand, the real one keeps turning, quiet, unbothered. True, it does not need our sketches, but it allows them. And in that allowance, in that grace, we find purpose. At the edge of sleep, where the lights dim and breath slows, it helps to believe the cosmos is sketchable, that behind the stars there is form, that within chaos there is structure. We began with a question, can we build a universe? Not literally, but in code, in spirit, in thought. Could we trace it gently enough to feel familiar? And along the way we did. We built galaxies in boxes, filaments in memory, stars in loops of logic. We saw beginnings, we saw ends, and through it all the quiet truth held firm. These are not the universe. They are ideas about the universe, and that is enough. Because models don't need to be perfect. They need to be honest. They need to wonder. They need to try. The most powerful simulations do not answer. They invite. And in that invitation, we find the next question. We find a reason to return. So, as you drift, remember, a sketch is not a lie. It is an offering, and even the roughest outline can hold a star. In the end, Maybe building a universe is not about control or precision or resolution. Maybe it's about listening to silence, to uncertainty, to possibility. And maybe in each run, each try, each digital whisper of what might be, we find not just galaxies, but glimpses of ourselves.